Hey, so thanks again, Halitha. This is a really interesting problem. Again, a little bit different from the previous one. And what this calls upon, at least in the first two parts, is a bit of an understanding about what makes vectors parallel and non-parallel. So for part A, crucially, we've got two non-parallel vectors, u and v, and they satisfy the equation lambda u plus mu v equals 0. And both of these are real numbers. And so what we need to prove, and I'll just say required to prove, is that not only are lambda and mu the same value, but that they also equal 0. Importantly, when we consider the fact that they're non-parallel, what this means is that you can't get u from any kind of scalar multiple times v. That's kind of what the non-parallel component means there. So we can't have that be the case. But if we come back to this equation here, our one in blue, for this to be true, what this would have to mean is that lambda u equals negative u v. And since u and v cannot be equal, the only way in which we can get this is if lambda is 0 and mu is 0. In other words, we can't actually have a scalar multiple bring this one to a point where it equals this one. That's what this kind of theory with non-parallel vectors is saying, is there's no kind of expansion or compression of those vectors that makes them equal to each other or shifts them into the right position where they overlap. And so because we can't get that, there's no manipulation of u and v that can make them equal without them being 0 vectors. And so from that, we can say that lambda has to equal mu, which has to equal 0. And I have to understand that's really theoretical. But it comes back to this concept of, okay, what is a non-parallel vector? And part 2 here uses the same concept. Again, they're non-parallel vectors u and v, and they satisfy this equation here. And so I'm going to write out that equation just to start with. And I want to try and use a similar concept to part A, but what I need to do first is actually collect like terms here. So I want to get the u's on the same side, and then I want to get the v's on the same side and collect them as like terms. So what that would look like is we'll have lambda 1 u minus lambda 2 u. And then on the right-hand side, it's going to be mu 2 v minus mu 1 v. And then you can see here that, okay, well, we've got a common factor of u, the actual vector, outside of lambda 1 minus lambda 2. Similarly, over this side, we've got v out the front. Lambda 2 minus, mu 2 minus mu 1. Cool. And so now we're at the point there where we're back to proving this concept. And that is, can this vector with any scalar multiple applied equal this other vector? The answer, no, it can't, because of this property of non-parallel vectors. And so this equation can be true, but if and only if both sides are 0. Meaning that lambda 1 minus lambda 2 has to equal 0, and mu 2 minus mu 1 has to equal 0. Therefore, we can prove our statement that lambda 1 has to equal lambda 2, and mu 2 has to equal mu 1. All right, so in part 3, it actually starts to get really hard here. And I think trying to wrap your head around the geometric understanding is really important before you get too deep in the problem with this proof. So I really like just setting an origin. I like having a reference point so then I can use position vectors instead of overwhelming myself with a bunch of letters. SB, SC, BC, CK, SK, whatever, right? So I've just defined S as the origin. Then from the origin, SB is B, SC is C. So B over here, C over here. Furthermore, that must mean that to go from B to C, we've got to go BS, SC. So it's going to be C minus B. So that's how I've defined BC here. Or, yeah, BC. And in light of the two position vectors I've used, this line S to K is a quarter of B minus a third of C. Sorry, plus a third of C. Yes. And so what we're proving then in terms of these new position vectors is that BL, so this length here, is 4/7 of this entire length, B to C, which I've defined as C minus B. What's tricky about this is that SK is defined, but not SL. And so we know that L is an extension of the line SK, but the actual values that we've got for SK doesn't extend through to L. So how I want to interpret SK is that S to K is the direction vector for the line connecting S and L. What that means is that we can convert SK to create the vector equation of a line that satisfies S to L. A vector equation of a line here is going to be obviously in the form R equals A plus KD. This D term is going to be the direction of SK. We already know this. We know that, and then A, sorry, can be our starting point, which is S in this example. So I can rewrite this to say that the vector of a line here that has a direction of SK and starts at S, in other words, the direction of our vector from S to L, from S to L, or in other words, simply just L, because S is our origin, is going to be our starting point, which is S, which we don't know, plus some scalar times our direction vector, which we know to be this. So quarter B plus a third C. And so I'm just going to redefine these vector equations of our lines here. It's not quite L because we're looking at it like a parametric form. So I'm just going to say this is R1 of the line that runs through here in some length, and the line that runs through this way I'm going to define as R1 for our first one running from S to L, and our second line running through BC, again, has to have a point on the line. We can say that that's vector B. And a direction, we're going to use, I'll use T here, a direction which is B to C. And we're going to define that as C minus B due to what I've got up here. Cool. And with that now, we have our two lines and we know that they intersect. So L is the point of intersection. Yeah. And so we can use our two lines to determine the exact position of L. Now, because we made S the origin, we can assume that the point from something to S, so position vector S here, is actually just 0, 0. So we can say R1 equals just K outside of a quarter B plus a third C. Similarly, R2 here, I want to expand out a little bit because we've got a like term of B here. So position vector B, let's just leave it like that, and then that's T times C minus T times B. And so we get 1 minus T outside of B plus T. Line 1 must intersect with line 2 at L. And so we can say that these two must be equal at some value for their scalar multiples. So what that would look like is that K, or even I'm going to substitute the K in. So 1/4 K times B plus a third K times C has to equal 1 minus T times B plus T times C. And this is kind of the important fulcrum here, is that now it's really difficult to see, but we've actually got simultaneous equations for B and for C. And so taking that outside of the context now, we know that 1/4 K has to equal 1 minus T. We also know that a third K has to equal a singular T. And so what we can say is, I guess first of all, we know that, well, we can solve both of these for T. If we just step back and take stock a little bit here, what we're actually trying to solve primarily for is T. Because what that tells us, C minus B represents BC, right? And that's this entire length here. If we find by what scalar multiple we have to travel along BC to get to L, then we know, okay, what's the ratio of going from B to L compared to B to C? And hopefully we can prove that's 4/7. So with our simultaneous equations here, we've got a ready-made substitution. So I'm going to sub equation 2 into equation 1. And that will get us 1/4 K equals 1 minus 1/3, okay? We can then move the K's to the same side. So that is 4K plus 1/3K plus 1. Take K out front. It's 1. We can then condense our denominators there. So we're going to get 12 plus 12. It's going to be 4. It's going to be 3 equals 1. So K, or 4/12 of K, equals 1. So K equals 7/12. If we then bring that back into our expression for T, we can say that T has to equal 1/3 times 12/7, which if we cancel these out, will give us 4/7, which means that if T is 4/7, then the equation of the line, that goes from B to L starts at is position vector B plus 4/7 of the line BC, meaning that the line BL has to be 4/7 times the line BC. All right, so 4 is similar again here, that we're using the vector equation of a line to create our proof. The first thing I want to do, and it seems like it's illegal, but you can just switch it around. It's a whole new question. So I'm going to say for question 4, let point A be the origin here, actually. And then again, I'm going to redefine point P, or the position vector of P is therefore -6 times the position vector of B. And importantly, these two questions are completely distinct. We're not using the position vector B here as the same position vector B in this question. I just want to make that clear. And then we're subtracting 8 times our new position vector C. So that's position vector P. What we want to find is, okay, does this position vector satisfy the equation of the line A to L? So if we remember here, A to L, well, we don't need to even go back to the last question. We could, but the only thing we need to take from it is that BL equals 4/7 of BC. What that means is that if we know AB and we know AC, and so in this example now, we're not looking at B and C there, we're looking at C here and B here. We can agree that to go from B to C, that's going to include B to A, A to C, which is C minus B. So again here, funnily enough, B to C is position vector C minus position vector A. Sorry. No. That's position vector B. Okay. And we know that B to L from the last question is therefore 4/7 of that position vector. So if we then are looking at the line A to L, the direction of that line, we're going to have to go A to B plus B to L. So I'll say A to L has to be A to B, which we know is position vector B, plus B to L, which we just defined. And we can simplify this a little bit because we can expand this out. And so here we've got 7 on 7B. Minus 4 on 7B. So overall, that's going to be 3 on 7 times B plus 4 on 7 times C. You could even, if you wanted to, say that that's, okay, 1 on 7 outside of 3B plus 4C. That's fine as well. And so that is, what this represents is the direction that you travel on the line A to L. In other words, this is the position vector L. in our part 4. If we're then looking at, okay, could it be on the line A to L? We need to figure out, all right, does it conform to the vector equation of a line that could be constructed based on this line A to L? And remember, the vector equation of a line is in this form, meaning that we would have to have this is a line from that has any kind of direction A to B and starts at A. So we can look at, okay, point A is just 0, 0 again here. So R is actually just K outside of, or even I guess you can write it as this, outside of 3B plus 4C. And that's the entire reason of why we make A the origin, why I at least think to make A the origin. Because otherwise you've just got an extra position vector you've got to deal with in every single scenario. And so this to me would be the equation of any point that lies on that extended line. So then what I'm going to do is say, okay, can we find a solution for K which lets us put this point on this line? Okay, and here again, if we want to equate our terms, we've got to multiply through by 1/7k on the right. So we're going to keep the left-hand side for now and multiply through by 1/7k. So that gives us 3k on 7 times b plus 4k on 7 times c. And now we can equate -6 to 3k on 7 and -8 to 4k on 7. So equation 1, -6 has to equal 3k on 7. Therefore, -42 equals 3k. Therefore, k equals -42 on 3. And that should have a common factor of 14. So -14 in the first instance. In the second instance, we've got -8 equals 4k on 7. That's going to be -56 over on this side equals 4k. Therefore, k has to equal -56 divided by 4, which likewise gives us -14. And so what that suggests is that on this line A to L, there is a value for k which satisfies the equation of that line being -14. What is interesting though, and I actually I'm not sure what the answer is here. The point AP is a scalar multiple of the line AL. So if by the line AL, they mean the vector equation of that line, which can have continuous values due to a scalar multiple, then yes, it does lie on the line. If by that they mean just the line segment A to L, then no, it doesn't lie on the line. Because what would have to happen to get position vector AB to be on that line is you have to multiply it out 14 by 14. So you stretch out that length and you flip it in the other direction, which is not going to sit within the confines of this actual line. So it depends on what the argument is here, to be honest. And I think this might just be my poor understanding of it. But if we're showing that it has to actually lie on the line, then the k value that we would need in order to fulfill that means that the line would have to be larger than it is. So even though it's on the right trajectory, it doesn't sit within that actual line segment. So it satisfies the kind of overall parametric equation, but it doesn't satisfy just the simple, okay, is it one of these dots? You know, it's like a dot out here. So in terms of justification, my interpretation is that no, it doesn't sit on the line, despite the fact it satisfies the vector equation of lines with that direction. That may be wrong. So that's something that I'd really like for you to check, and just maybe leave a comment down below as to what your findings were there, because I'd be really interested there. But that's how I do these questions. To be really honest, they're quite difficult. So A and B, like parts 1 and 2, that comes back to the theory of them being non-parallel vectors. Parts 3 and 4 then are actually quite difficult vector proofs involving the vector equations of a line, and finding the intersection between them. But I think the key part that I've done here is actually moving the origin to a point that gives us less maths. So yeah, I'd really would be interested to see what the answers were for those questions, if you've got them from a textbook or whatever. Because yeah, these were tough to work through, but glad I can help you. And yeah, I'd really appreciate it if you could maybe even like this video if it was something that you found useful. And yeah, feel free to submit any more questions you've got to us whenever you need. Thanks so much.